Okay, so question 5 begins with a very standard bond enthalpy question. So this is a really important type of thing to be able to do because it comes up all the time, and they should be easy marks if you just learn the method. So the first thing, remember, is that you should, I would strongly recommend, draw out the displayed formulae of all of these so that you can keep track of all of the bonds that are there. This is a relatively simple one. You can probably get away without doing that if you're very comfortable with all of these things, but it's terribly easy to miss out a bond or count one twice or whatever. So what I would always do is draw out the displayed formulae. So that's what we're going to get for carbon dioxide, plus 4H2, so that's 4 lots of HH will give you methane, plus 2 lots of HOH. Okay, so the advantage of drawing it out like that is that when we now add up the bonds that are broken and the bonds that are formed, we can sort of tick them off as we go through and say, yeah, I've taken account of those, and that should minimize the risk of messing any up. Now the way you approach this is always to make a separate subtotal for the bonds on the left hand side and the bonds on the right hand side, because apart from helping you make sure you get the right answer, that's usually the way the mark scheme is set up, that you get individual marks for those, even if you then sort of mess up somewhere along the way. So that's the way to get the marks for working. Okay, so we get the bonds broken first of all, and you can see that we have 2 C double bond O's, and that will be 2 times 805, and we have 4 H single bond H's, which is 4 lots of 436, and if you add that lot up on your calculator, you should get 3354 kilojoules per mole. And then we do the same for the bonds formed, which are the ones in the product on the right hand side. So this time we have 1, 2, 3, 4 CH's, which is 4 times 415, and we have 2 OH's in each molecule, so that's 4 OH's altogether, which is 4 times 464, and that comes to 3516 kilojoules per mole. Okay, so those are our separate subtotals, and then you have to remember what you have to do to combine them. So remember, bond breaking is endothermic. That's an incredibly important point, that you always have to put energy in to break bonds. You always get energy given out when you form bonds. So you shouldn't have to learn some arbitrary rule for this. If you've got that basic principle sorted out in your head, then you know what to do, which is that you say, right, delta H, so we've got our totals here, and you say delta H is equal to plus the number for the bonds broken, because it's endothermic breaking those bonds, so positive delta H contribution, so plus 3354, and then it will be minus these bonds that are formed, because that much energy is given out, so minus 3516, which is minus 162 kilojoules per mole, is the right answer. Okay, so make sure you've got the signs the right way around there, and as I say, the best way, rather than just learning it as a rule, is to think about it. Think, when you break bonds, you put in energy, so it's endothermic, so it's positive. When you form bonds, you give out energy, so it's exothermic, so it's negative, and that way you're much more likely to make sure you get it the right way around. Okay, so part B then just deals with a couple of these climate change related issues which you need to be confident to talk about. So first of all, you have this what sounds like a horrendously complex question. Explain how atmospheric methane molecules can contribute to global warming. In fact, when it says that, it wants only the very simple idea, first of all, that they do that by absorbing infrared radiation. And that would be true whether it asks about methane or carbon dioxide or indeed water vapor. Okay, so the first point is that they contribute to the warming of the atmosphere by absorbing infrared radiation. And then for the second mark, you have to explain what do they do with that energy that they absorb, and the answer is it makes their bonds vibrate. And that's it, that's all you need for 2 marks. Ions absorbed, bonds vibrate as a result. Okay, second part of that, carbon capture and storage. You need to know the 3 strategies that have been contemplated for doing that. So they are, first of all, injection in the deep ocean or on the seabed. That would do for one. The second is injection into rocks, for example into disused oil wells, so that you store the CO2 deep in the rocks. And the third one is reaction with naturally occurring metal oxides to form carbonates. Those are the 3. Any 2 of those would be fine. Okay, so on to part C, which is the radical substitution mechanism of alkanes reacting with halogens. So this is again one of those set piece mechanisms that you need to have learnt, and this is a very small step from the methane plus bromine one that you've learnt originally. We're just stepping up to the next alkane in the series, ethane plus bromine, but otherwise it's the same thing. So you've just got to go through, write out the mechanism, which you hopefully will have learnt in detail, and make sure you've ticked off all the specific points that it asks you to address. This particular mechanism, the radical substitution one, again is one of those things where I would tend to break the rule of wanting you to use structural formulae. I think with this one they're always going to be happy with molecular formulae, and it makes your life much easier if you stick with those. So that's what I'm going to do. But remember, this is the exception. Normally in organic chemistry you should think structural formulae are the best way to go. Okay, so the overall reaction of bromine with ethane is C2H6, that's ethane, plus bromine, and remember it's a substitution reaction. So hydrogen comes out so that bromine can go in, so you get C2H5Br, and HBr is produced as the other product. Okay, so that's the overall reaction. And then the mechanism, the first step is called initiation. Okay, and you need to know the names of these steps, and indeed it asks you for that as one of the, as your third bullet point there. So the first step is called initiation, and that's simply the bromine breaking up into radicals. So Br2 broken up to form 2Br dot, and that's the step that needs UV light. Okay, so that's the first step. When you do that, obviously you're breaking a bond, and what that dot indicates is that the shared pair that form the Br-Br bond, when you break it, each of them gets one of those electrons, and that's called homolytic fission. So you can put that in here. It occurs later on in the mechanism as well, but this is the first instance of it, and it's homolytic fission. You can explain that means that when the bond breaks, one of the participating electrons goes to one of the atoms and one goes to the other one. Okay, now we move on to the second stage, and this is where the main part of the reaction occurs. This is just what you need to kickstart it, but the reactions which actually add up to give you this as your overall process occur in the second stage, which is called propagation. So again, you need that word down here, and there are lots of ways to remember this, but the simplest, I think, is to remember that what radicals tend to do in this mechanism is when they collide with a molecule, they pull one atom out of it and react with that to form a new molecule, and that leaves behind a new radical. So we've got Br dot, that's our reactive radical that's coming in. It's going to collide with ethane, C2H6, and as I say, it pulls one atom, one hydrogen out of there, and that gives you HBr, and what it leaves behind is C2H5 dot. Sometimes they're not very fussy about the dots, and you, in this particular paper, actually could have left them out entirely and they wouldn't have cared. If you do put them in, you should put the dot at that end to show that it's a carbon that has the unpaired electron rather than the hydrogen. Okay, that's the first part of propagation. We've now got a new reactive radical, C2H5 dot, and again that will bounce around until it collides with something it can react with, and if it reacts with bromine, Br2, then again it pulls one atom out of that Br, out of that Br2, which gives you C2H5Br, and that leaves behind Br dot. Okay, and those two reactions follow one another as a chain reaction. And again, it's worth spelling that out, that that's a chain reaction, because the first one generates the ethyl radical C2H5 to fuel the second one, that generates Br dot, which fuels the first one, and so they can go on following each other a very large number of times, many thousands of times for each initiation step that takes place. You can tell that it's right, because if you add the two together, they give you the reaction at the top. And it's worth remembering that that's what should happen, so you can tell whether your propagation reactions are correct, because if you add the two of them together, cancel out the things that occur on both sides, so the two Brs will cancel out and the two C2H5s will cancel out. What's left is ethane plus bromine, which is your left hand side there, goes to HBr, plus bromoethane, which is your right hand side there. So it shouldn't just be a random process of just trying to put something together. You should remember propagation adds up to give you the overall reaction. The third stage is called termination. And this is not something that's necessary for completion of the reaction. This stage completes the reaction, but it's something that complicates it, which is that when two radicals meet each other, there's the possibility that they'll simply combine together and form something with paired electrons. And of course, once that happens, you haven't got a reactive intermediate anymore, and it stops the chain. So you have to keep the light on all the time, otherwise the reaction will stop after a relatively short time because of these termination steps. So there are three possible steps, and it's worth writing them all down. So you can get two bromine radicals reacting together to give you Br2. You can have a bromine radical reacting with an ethyl radical to give you C2H5Br. And in terms of outcome, those two aren't very interesting, because this just regenerates a reactant. This produces a slight extra bit of the product. The interesting one is the third one. If two ethyl radicals react together, then you'll get C4H10, which is butane. And that's the one often that they will ask you to focus on, because obviously explaining how you get this doubling of the number of carbons in a molecule is something that is sort of a special feature of this mechanism. So you'll get a trace of butane being formed. Okay, so that's it all written out, and we just have to check that we've talked about the type of bond fission. Yes, we have. Homolytic fission. We've given equations for each step. Yes, we have. And we've named each step. So that's fine. That's all we need for that part of the question. Okay, so the last part is asking us to explain how come you get more than one organic product in this reaction. So what we've written down so far just produces bromoethane. But notice in writing out one of those termination steps, we also produced a second organic product, which is that a small amount of butane would also be produced, and that would do for one of the reasons why you get multiple products, because of the possible termination steps. The other one, though, is that remember that there are 6 hydrogens in an ethane molecule, and we've just replaced one of them, but there's no reason why the other ones couldn't be substituted as well. So the next point is that more than one bromine, or variable numbers of bromines, can be substituted into the molecule in place of hydrogens. And of course, once you've got more than one of them, you get possibilities of isomers. So for example, you could get 1,1-dibromomethane or 1,2-dibromomethane. Okay, so the fact is that you can substitute variable numbers of times and at variable positions, and that's what gives you the big diversity. So for that reason, radical substitution is not generally a favoured way of carrying out reactions, because you tend to get a low percentage yield of any particular product, because lots of these other ones are produced as well. And it's worth remembering that that's, you know, an important limitation of these kind of reactions in practice. Okay, and that's it for question 5.